As I mentioned uh, last night, I think, in an email, just talking with some students, realized that maybe there was a little bit of confusion on the assignment. So, wanted to clear that up and then give you a chance to incorporate anything I say today. And so I've extended the due date on that until Sunday evening, Sunday night. So I've also assigned a new one, and I'm you know there's a few things going on. We have our midterm exam scheduled for the uh, is it the 5th? Yes, the March 5th. Midterm grades are due on that Thursday, so we've got to get another exam in, and so we'll do that, and then I'll grade that real quick and get your grades in. So that way you'll have, I think, 5 assignments, and that first test was, kind of somewhere between a test and a quiz. And then the midterm is actually a bigger component of your grade. So hopefully, uh, hopefully everyone will be successful at that and understanding a little bit about where I'm coming from. So last year when I taught this course, we did more kind of traditional homework assignments, and you'd have to work through computational problems and that type of thing. This year, as you know, I'm emphasizing more on MATLAB. I think that will serve you well in the long run. And but it does kind of keep, have kind of leave that, uh, problem solving of a computational nature, or basically by hand, kind of open. So hopefully next week, I'm going to go through a couple of problems in class. And these were from homework problems that I had assigned last year. And so I'll go through that, and then hopefully that will give you something to study for, and be able to do a very similar type of problem sets on the exam. It's difficult to do the whole MATLAB thing. So let me show a few things here. And so on the um, on the current assignment, there's just a little bit of confusion. Let me get logged in here. So one of the questions ask you to switch to gray coding. And I should have been a little bit more careful about wording that, because as it turns out, gray is the default here. On if you look at, this is the MATLAB help page for the QAM mod, right? And of course, there's a corresponding Comm D mod, right? So we could look at this, and it also has this symbol order parameter in here, right? And so they do give some examples here with the QAM symbol ordering, and here they show, so this is in decimal form instead of binary form, but that's 0, that's a 1, so that would be like a 0001, and so on, right? So here's a 2, so this would be a 0010 in binary. So you can look at this, and it's hard to see in the decimal form, but if you switch this to binary, then you will see the the binary digits written out on these constellations, and it'll be a little more clear that only one bit is changing between any of the closest symbol locations, right? So only one bit changes. So the point I was trying to make here is that you need to match up both the modulator and the demodulator, because otherwise the demodulator is going to interpret symbol locations and map that to incorrect decimal locations, right? So the receiver might be figuring out the right symbol, but that mapping has to be done consistently also. So the way it's written is kind of assuming you did this binary symbol ordering at first and then switch to gray coding. So if you just use the default, you were actually using gray coding in the beginning. Doesn't really matter. Just at some point, in that where I'm asking you to change that, swap the receiver and the transmitter, or the modulator and the demodulator, in terms of the symbol ordering, and you should see the error increase, right? Even with no noise in your system, the error is going to be significant because of that mapping. You do that, that's enough. So you don't have to, if you've already done it with the default gray coding at the beginning instead of the binary symbol ordering, no need to redo any of your work. Just show me that, yeah, you understand that concept, right? When you do present your results, it's good to maybe make it easy for me to see what chart or what computational lines go with what question I'm asking there. So do that in the comments or something like that. Oh, why am I not able to do this? Let's so the other thing is, I wanted to make sure everyone understood how to get to the waveform generator. That's the last part, and all that I'm looking for there is to show you how okay, I can't do my password and talk at the same time, apparently. So what I'm doing there is having you just work with more MATLAB tools. It's not anything hugely dramatic here. Some of you all are familiar with Simulink, and that's great. And we often use Simulink in communication system modeling. In fact, a lot of times what happens is, well, in my work, my workflow that I like to do when I'm consulting or working on a project is I'll develop my algorithm in MATLAB. Then I'll move to Simulink, and Simulink allows us to get timing accurate and ultimately bit accurate. So in MATLAB, you can, so a lot of times when we're doing signal processing of communication waveforms, we're doing it in integer math. So we'll have, let's say, a 14-bit ADC and DAC type pair, and that's going to give us a certain number of bits, right? 14 bits or something like that. So we will do our calculations in that resolution, maybe a little bit more, but we might be doing an FPGA or a DSP and using fixed point math. So we can actually simulate that in MATLAB and in Simulink by specifying that the calculations are done in fixed point integer math instead of floating point math. And so you'll have some different types of round off error that shows up as quantization noise. Not sure if you've seen quantization noise in one of your maybe embedded systems or that type of thing, but it's the noise that it arises because you're not using an infinite number of bits to quantize your signal, right? You're using a finite number of bits, and that quantization noise represents that kind of gap between the bits, right? The bit levels. Then we'll move to Simulink, and Simulink allows us to be timing accurate, and we can even use like some tools from Xilinx or which is now AMD. Who bought Xilinx? I think AMD bought Xilinx, and then Intel bought Altera. They actually bought them first, and so that they have tools that allow you to plug into Simulink their actual cores that they have in their FPGA, so you can get very, very, very accurate. We're not going that far, but there is a handy app, and you can do this waveform generator by going to apps on this tab up here. And then it's actually called wireless waveform generator. So you fire that up, click on that. And it's just a tool that MATLAB builds in. You generally got to pay a little bit more for some of these things when you buy them yourself, but they're pretty handy little tools. And I'm waiting. Okay. Looks like it's going to come to life here. So now it comes up, at least when I do it, is with a default of this OFDM. Now that's a more sophisticated type of waveform that's used in a Wi-Fi and LTE and 5G type communications. It's actually used in HDTV and a number of other things, right? So we'll get to that at the end of the semester. But I think, did I say PSK or Comm? Maybe I think I said to do it with PSK. So choose the right constellation or the waveform mapping, right? And then down here in your tool window, you can change the modulation order to 8, and you can see you can change the symbol mapping here, and you can do this user defined bit source. Now here the input bits are going to be random integer values, and it's got it at 60,000. So we could, and it's going to be producing integer values of 0 or 1. So it's basically bits. So you can do 10,000, you can do 60,000 as a default or whatever, right? And then there's a rate. We haven't really done anything about that. We haven't talked about filtering conditions yet. That's coming up in a few weeks. Maybe right after the exam, we start talking about band limited channels. So the other thing you need to do is come over here and click on impairments, and then you get an opportunity to click AWGN and plug in your SNR. I think I said 12 or something like that. You can still open up waveform and that type of thing. And then over here, you click generate, and it'll actually run through all these different things, and it will show you the time domain of both the real and imaginary. And down here is your spectrum analyzer, and here is the constellation. So you can do a screen grab of this, or maybe you can print this out. I'm not sure if it allows you to print this. Not really. So, but just noting here, looking at this constellation. And so while we're here, so what we see is that noise makes it really hard to isolate what symbol was actually sent at the receiver, right? This is what the receiver sees. And here at 20 dB of SNR, it's pretty easy. But at 12 dB of SNR, it's starting to get a little messy, right? So there was another thing. If we go here to Comm, and with a modulation order of 4, let's run that real quick. And we see that's pretty easy at even at 12 dB. It looked pretty messy in PSK, but here in that was an 8 PSK, right? So this is a 4. Now, if we change this to 8 and run it, okay, maybe a little harder to distinguish, right? Just like we saw in the PSK situation. If we go up to 64 QAM, which is, I think, what I'd ask you to do in more of the manual type calculations, we see, look at how ugly that is, right? There's 64 different symbol locations. So look at this guy that's way out there, right? So that's a pretty low probability that it happens, but it certainly can. Even at 20 dB, we're going to see that it's still a little messy. If we go up to, let's say, 40 dB, now it looks pretty clean, right? And we can up this to give us more points so it's a little bit clearer. At 40 dB, there's hardly any noise and it's really easy to see. But even at 20 dB, it's messy, right? So that's that trade-off. At with 64 QAM, we're sending lots of bits per symbol, right? But our noise immunity has gone way down, right? So, all right, so that's hopefully gives you an idea on how to deal with the homework assignment. And so I did add this assignment. So this is kind of the next step, and we'll talk about this. You'll start to see how to do these assignments in today's lecture, hopefully. So if we don't get that far, then we'll deal with it. But you're basically going to use the Q function, which MATLAB is shown here. It's evaluating that Q function we talked about on Tuesday, right? So, and we're going to basically develop a relationship for different types of modulation schemes in terms of the signal noise ratio, or more specifically, the energy per bit per noise power spectral density, EBNO, the energy per bit, and the NO, which is just normally written capital N, lowercase o, for the noise power spectral density. We actually write as N naught over 2. But when we write it out as EBNO, it's typically lowercase or all uppercase, whatever. And so we might put that in terms of dB. But of course, when you do calculations, you'll normally want to convert that to linear, and they give you a little bit here. They're doing it in terms of QPSK. We're going to do it in terms of BPSK, or binary antipodal signaling. And so this equation changes slightly. There's no factor of 2 there, but note that you start off in dB and you convert it to linear magnitude, right? And these are powers, and so you divide by 10, not 20 like it would be in terms of amplitude. No, these are powers, so you use 10, and then raise that to the power of 10. Then you plug that in as this EBNO, right? So this is what this is standing for, the energy per bit per noise power spectral density, right? So that's what it looks like in a formula. That's what it looks like when we write code. And so then you're just evaluating the Q function, right? So, um, and you should get some reasonable results, right? And then I'm going to ask you to do it using the modulator and demodulator and EWGN that you doing for assignment 4 that's due on Sunday night. And so then you're going to plug it in. You're going to do maybe 10,000 points, maybe 100,000 points. Run it, calculate the number of errors at your error rate, which is essentially your probability of error. See if those match, right? Okay, so let me change windows now. So hopefully that makes sense, and it'll make more sense when we actually get to those calculations. All right, so another little thing, I think last Tuesday, kind of prepping for lecture, I looked at this slide and I put in this also defined as f of x, capital F of x as a distribution. And that was actually wrong. And when I got to this slide, I'm like scratching my head because here we're doing this, this f of x is not equal to q, it's equal to 1 minus q. And the reason here is f of x goes from x to infinity, whereas this q, see, I'm these integration f of x, I'm sorry, is this minus infinity up to x, whereas q is x up to infinity. So one is going to be, you know, one side of this PDF curve, and the other one's going to be the other side of this PDF curve, right? So f of x is below this you know, point here, and in this graph it's shown as y. So that's that probability that your random variable lies below or less than this particular value, whereas a q is looking at this tail right there. So sorry about that confusion. This slide was correct though, and other than me putting in that f of x in here, this equation was correct also. So I've corrected this slide here. All right, so we talked about the Q function and showed that basically you can look up these parameters. You can look up the argument x here and then get out the Q value. And so then I think this is about where we finished up, and we started talking about decision areas, right? So if these are your ideal symbol locations, then how do we map wherever our signal is received after it's been corrupted by noise or other effects? How do we map that optimally to the symbol location? Well, when you draw it like this, it looks pretty easy, doesn't it, right? So it kind of makes sense. Let's go through the mathematics of it, and then we can also handle more complex type situations. So let's first define a set of decision areas, D1 up to D cap M. Again, M is this order of, you know, how many symbols are you sending in your symbol set, right? And it's related to the number of bits that you send per symbol, right? And so you're at any given time, you're sending one of M different symbols, right? So we need M different decision areas to try to figure out when we look at a receive signal, what does that mean in terms of helping us estimate the our best guess at the sent symbol. Right, so M hat here is our estimate. M is kind of the ground truth. This is what was actually sent. Of course, at a receiver, we don't know what was actually sent. And so all we can do is look at R, process that through some function, and come up with an estimate M such that it's more as often as possible actually equal to M. Right. So um, the uh, so we can say this d sub little m, right, a particular m, is going to be equal to, where this r is drawn out of this n-dimensional set of real vectors. Okay, and this is a little bit of area that we have kind of done a little hand waving over for the sake of time mostly. And but if you did this course as a graduate level course, you would go into a little bit more rigor on uh, representing our time based function r of t, right, as a time based function, and we would describe that in terms of this orthonormal basis set, where now this r, this vector r, would be the coefficients of that basis set that best matches that r of t, right? So here we're looking at a vector instead of this function of time, r of t. And the same thing with sm also. So we're representing that in an n-dimensional real space. So there'd be n terms in this vector here. And so what we're saying is that we're going to map to a particular dm where the probability of m have been sent, given that we received r, is greater than the probability of any other m prime not equal to m for r, right? That makes sense, right? So we want to, given that we received r, what was the, maximizing the probability, and choosing that for our decision area, and then mapping that to this m hat, right? And so we need to do that for all the m's in between 1 and cap n, right? So here there's an example of 2, and I've just kind of drawn these decision areas based around maybe the, if we call that the x-axis, x equals 0 axis, right? So conceptually, we want to choose these boundaries, right? So this boundary here, let me get my laser pointer up, right? So we want here's this boundary, right? Boundary between these decision areas. And if we receive a signal here or here or here or here, it's in this area, so we're going to map it to that symbol, right? Conversely, if we receive it over here, we're going to map it to that symbol, right? So we want to, choose the boundaries of the decision areas such that we give the receiver the best chance of selecting the correct message in spite of the noise and other impairments that perturb the position of the receive symbol relative to all of the other ideal symbol locations. So how can we derive a methodical approach at finding these areas optimally? All right, so now comes the math, right? So let's first assume an AWGN channel, additive white Gaussian noise. When we say that, we're allowing this channel to be corrupted by noise, but that's it, right? We're going to ignore all the other impairments. And so we say that our received signal is, as a function of time, is equal to the specific transmitted symbol, which has some time dependency, right, from maybe 0 to cap t or something, right, plus some noise over that time, right? So noise is now going to be some noise, function of time drawn from this random process that describes noise, right? So this entity at one trial might be have a certain shape in terms of time, and another time it might have something else, right? So, but it's going to be a Gaussian process, right? And so this is going to hold for any, regardless of what is sent for M, which symbol is sent. So we can use this kind of vectorization thing again and now write it in terms of vectors, where now we have this noise vector. And there's a little bit of hand waviness going on here that the book might go into details on, but as it turns out, we kind of go through a more sophisticated analysis to say that all those things don't matter, and we can still represent it as this vector, right? So the same basis functions that we're doing with the R and the SM. So this should also be kind of bold-faced, sorry. And so now, based upon the results that we looked at on Tuesday, right? So we derived this kind of relationship, this argmax, where we use Bayes' formula and that type of thing, right? So where we are able to flip the probability around between, or this conditional probability around, but we end up with this P sub M in front of this relationship. And this is the probability that the transmitter sends a particular symbol, right? So it doesn't necessarily have to be equal probable, right? We may have a communication system where we're more likely to send one symbol than another, right? So so we account for that here. And we want to choose the M that maximizes this relationship here, right? Where then this is a function of that M and this is a function of that M, right? So, and R is what we actually measure. So now we can do a little bit of shift here. So we're going to, so this is our map receiver, our maximal posteriori receiver. I can never pronounce that. That, and we looked at that on Tuesday, right? So here now we're going to, since this is an AWGN channel, we're going to rewrite this in terms of the probability of noise, right? So we look at this equation up here, and we see that SM is or the noise can be written in terms of R minus SM here, right? And then we can look at the probability of that noise, and so that's really what is making this a conditional probability, right? So then we note that it's Gaussian noise. So now we can write this probability of this noise process here and as a Gaussian function. But noting that this is an n-dimensional vector channel. So when we look at this, they're all independent noise. So they're just going to, here are the coefficients going to get multiplied, and this is going to get squared here. So I'm introducing a little bit of notation here where we have a geometric norm here, right? And then we go from here to here by noting that this term is not a function of this M, right? So when we're doing this argmax process, there's no M involved in here, so it's a constant, right? So it doesn't matter, it has no impact on this function. And so we can ignore it, right? So that's how we go from this step to this step. Then, yeah, we don't like this exponential, so we're just going to take the logarithm of both sides. Now, how can we do that? Well, the logarithm is an increasing function, right? So as the argument increases, it increases. And so it has no impact on this argmax. Now, the value of this argument is going to change relative to this because, yeah, we just arbitrarily took a logarithm there, but it doesn't have an impact on this process of figuring out which m actually maximizes this argument, right? Even though this argument now has been shifted in scale, it's still trending in the same way with respect to m. So we're able to take the logarithm of this, and using the property of logarithms, then multiplication is really addition once you take the logarithm. But since there's a minus sign up here, and it's an addition of a negative value, so the logarithm cancels out the exponential, so we're just left with the argument of the exponential there, and we're left with logarithm of the initial probability of which message is being sent. Okay, well, we're not done. So I just repeat that last line up here for context, and now we're going to also introduce this n naught over 2. It's a positive number. And again, this n naught over 2 is the power spectral density of the noise process. It is describing the variance in the noise, right? Or the amount of noise power. So we're going to multiply by this number, and that cancels out the n naught in this second term. But introduces this 1/2 factor there. And again, it's a positive number, so it's not affecting this argmax function. Then now we expand this guy out, and we end up with this type of equation, right? Where now this is the multiplying two vectors. That's a dot product type operation. Right. So let's look at this. Well, this R, the received signal, it's, we just measured it, right? So it's not a function of m here, right? So we can drop that out. Again, it doesn't have an impact on this calculation. So we're going to get rid of that. Then we're also going to recognize that this is the energy of the symbol, right? So we'll rewrite this as this EM for the energy of that symbol, right? So I think all the other terms are the same, this 2 and that 2, and the minus signs cancel out. So, all right, so now we're going to define this eta sub m, and we're going to use this to represent a bias term of this equation, right? So we're going to take these first two terms in this argument and just replace it with an eta sub m, right? So that's just a simple variable substitution and makes our equation look a little bit nicer, but also helps us understand that this is kind of biasing this argument right here. Okay, so but it's still a function of m, right? So we can't just ignore it. All right, so now this looks a lot friendlier, but what does it mean, right? So here I'm just kind of rewriting it, and this bias term skews the decision area boundary, right? So if the signals are equal probable, all right, so let's just say now that this P sub m here that we introduced to talk about the a priori probability of which symbol is actually likely to be sent by the transmitter. And we're going to say that all the symbols have an equal probability of being sent, right? So now each individual probability is simply 1 over capital M, however many symbols. If you got an 8-PSK type system, then the probability of any one of those symbols being sent is 1 over 8. If you got 64 Comm, it's 1 over 64. If it's BPSK, only 2 different symbols, then it'd be 1 over 2, 1/2 probability of one versus the other. All right. So now we're able to note that these guys are no longer functions of M. And so then we can ignore those and just focus on this, right? So this is only when the signals are equal probable, right? And I've kind of rewritten this dot product as that there. So then since we have a negative sign here, now we can switch this from an argmax to an argmin, right? So if we're got a negative sign in that argument, then we can just cancel that out by minimizing it instead of maximizing it, right? So now we have this type of relationship, right? So this is this distance metric. Distance being that now if we, okay, so this looks a little crazy, right? But we're just going to place 4 different symbols kind of arbitrarily in a 2-dimensional space. Okay. And now we're going to consider what are the decision areas. Now, you wouldn't actually do a constellation like this, right? This would not likely be a very optimal in terms of error rates or energy to send the symbols type of constellation. But it's helpful to kind of force us to think in generic terms or general terms instead of anything that's specific and taking advantage of a lot of symmetry like a lot of our constellations do, right? So again, this is where they're equal probable. So the decision boundaries are the loci of points equal distance from the nearest S of M, right? So here we would have this decision point, this decision boundary, I'm sorry, between this D1 and D2 over here. And we see that this boundary is equal distance from these 2 points, right? Regardless of whether it's out here or wherever, right? And so, and that's coming from this relationship, right? So we want that distance to be minimized, right? So we're going to pick the symbol that corresponds to M such that that distance between what we actually measured and where that symbol is minimized, right? So what M are we going to pick? Are we going to pick 1 or 2? Well, we want that distance to be minimized. And so that boundary is when they're the same, right? So if we're here, or let's just use the example here, right? So this is the closest symbol, right? So this is, find the SM with the minimum Euclidean distance, right? So I guess that's the term that was escaping my memory earlier when we write it like this with these double bars. So I guess I should point out that we can also drop this square here, because squaring this is going to give us a positive value, and then that's taken care of when we drop the minus sign by changing it to a minimum. So the decision boundaries, these solid lines, actually bisect the line connecting each SM, right? So again, this is because we're looking at this minimum Euclidean distance. So, excuse me, whatever type of constellation you have, then you would draw these lines connecting each pair of constellation points. We don't really need to worry about this one to that one, but because their decision areas don't connect to each other, right? But so the general approach is connect these different symbols, locations, the ideal symbol locations, and then draw uh, a, a line that bisects perpendicularly, right? So we're bisecting it because since we're equal probable, if we're on this side of that midpoint, then we're going to map to this symbol, right? If we're on this side of that midpoint in that line, we're going to map to this symbol. And, we want to be normal because we want these loci points to still obey that same minimum distance, right? So, so it's just kind of a simple methodical approach. Once it's equal probable, we connect these different lines, and then we draw these bisecting, right? And when we first draw it, maybe we don't know where all these things are going to locate, so we might sketch it out like that. And then we'll sketch this one out. Then we look at this one. Okay, well, we got to bisect this line too. And so we draw that. And then we look at this line, and we got to bisect that. And finally on this line, and we bisect it, right? And then we look at where those join, and then that forms our decision areas. So, right, so D1 is going to be in this region here. D2 is now formed in this region, right? And it goes off to infinity out here, but this is kind of the boundaries between these decision areas. D4 here is mapped in this by these boundary lines, and then D3 over here, right? And so this isn't two-dimensional space. If we would go to multiple dimensions, then we would really be dealing with hyperplanes and stuff. We call this a nearest neighbor detector, right? Because we're looking at wherever this R lands here, and I just arbitrarily do it right there, right? But it could be over here, it could be up here, it could be right there, it could be right there. We're going to the nearest neighbor using this Euclidean distance, right? With all these little double vertical bars squared and that type of thing, right? So that's falling out from this dot product type relationship. So, all right, so that's kind of the, I should be able to, on an exam, sketch out a somewhat arbitrary number of symbols in a particular locations, and ask you to draw out the decision boundaries and then label the decision areas, right? So your first drawing, your step one is to draw these connecting lines. Step two is to draw the orthogonal bisectors for those, figure out where they intersect, and then locate or label and kind of sketch out D1 versus D2. Right? So if this wouldn't get too messy. I might like draw in hash lines here and maybe show different hash over here and maybe a different color or whatever, right? So you should be able to then develop a receiver that would, wherever that R is measured at in this case two-dimensional space, then map it to the correct or the best estimate of the transmitted symbol. Again, all this applies when it's equal probable. All right, so here's the governing equation here, right? So that was the graphical interpretation of this type of this relationship here, but then if we now go back and relax this requirement that it be equal probable, then we actually have this bias term in here, this eta sub m, right? And remember, we have that defined here as this kind of logarithmic, with this noise power spectral density of the probability of what the transmitter would actually send, right? The probability of the symbols being sent and the energy of those each of those symbols, right? And so, and we recall in some constellations, all the symbols have the same energy, right? In a simple PSK type constellation where all the constellation points are all distributed around a circle of constant radius, then they will all have an equal energy. Contrast that to a higher order Comm type thing where those symbols kind of nearer the origin of this maybe 64 Comm type of constellation, they're going to have lower energy than the ones at the outer edges, right? So, all right. So here's the general rule is that we want to, determine a decision area for each symbol where our vector R is out of this n-dimensional real number space, right? And we say that this M is going to be where this dot product of the perfect, unperturbed transmitted symbol is dotted with the actual received signal vectorized, plus this bias term is greater than any other option, right? For any other M prime not equal to M. So that's going back to this equation here. Okay, so this equation describes the decision areas for each M in terms of the received signal vector and the bias term and maps to a particular M and therefore transmitted symbol. Right? So let's consider an example of a binary antipodal signaling. All right, so it's a kind of a fancy terminology. You'll recognize this as essentially BPSK, binary phase shift keying, or PAM, pulse amplitude modulation, with maybe some more restrictions than just that terminology would indicate. But since it's binary, we have a k is equal to 1, so each input bit maps to one of two different symbols, right? So 2 to the power k to the power 1 is M, so there's two different symbols, right? And so we call it antipodal because one's going to just be the negation of the other, right? So if this S1 of t is equal to S of t, some symbol shape over time, some pulse, right? Then S of 2, the other symbol, is just going to be the negation of that, right? That's what we mean by binary, by antipodal, right? So it's binary, meaning there's two different symbols, antipodal meaning they're equal but negated of each other, right? So now we're going to also relax it and say it's not necessarily equal probable. So we'll call this P sub m, where m equal 1, right? So the probability of the symbol 1 being sent is represented by this little p. And since the total symbol set is 2, you got to send one or the other, right? Then that means the probability of the other symbol being sent, this 2, is simply 1 minus p, right? So something's got to be sent, right? So there's probably a 1 that one or the other is going to be sent. So if probability of 1 is p, then a probability of 2 is 1 minus p, right? And we're going to note that here the dimension, this n, is equal to 1. So we're going to lie on a line, not in the complex plane. In terms of the symbols, right? So we can now represent these as vector representations. Now, again, there'd be kind of a basis function, and you could use this Gram-Schmidt normalization process to come up with the particular basis functions, but based upon these this S of t here. But it's going to S here is simply going to be the square root of the energy for that symbol. And here the amplitude S2 is going to be minus the square root of this energy of the symbol, right? So here these these guys represent amplitudes that are being set. So since k is equal to 1 here, it's a binary system, then there's one bit maps to one symbol, and so the energy in the symbol is equally energy in the bit, right? So there's equal allocation there. So now we can write D1, decision area 1, where given that we receive R, then we want this relationship to hold, that we've got, this is coming from the bias term, right? Because we're not necessarily equal probable, right? So this comes from the bias term, and then this comes from the S1s and S2s here, where they're actually, I'm sorry, this second, that the second and third term are the bias terms, whereas this is that dot product term, right? So we're R times the S, right? So, and since n is equal to 1, that dot product is trivial, right? So it's just the single dimension values being multiplied by each other. So these are the bias terms there, and same thing over here. So what we see here is that this negative comes from this S2 right there, right? So our D1 is going to encompass everywhere that this side of the equation is greater than this side of the equation, right? So what does that look like? Let's try to interpret that here a little bit, right? So I'm just repeating that there. Now we can rearrange some terms here to make it a little bit easier to interpret, right? So now we're going to try to gather up terms on each side. So bring this guy over here and add to that, and this guy on the other side, and so on, right? So these guys cancel out, right? They're both negative, so when we pull it to the other side, they're going to cancel out. These guys don't, right? Because the arguments are inside this natural logarithm. Logarithm here are different, right? So this is probability of this guy being sent, S2. This is the probability of the other one being sent, this P here, right? And so, but subtracting logarithms, right? So this term minus this term is equivalent to dividing the arguments, right? So that's property of logarithms. And so we've got same coefficient there. And then so instead of writing it out as natural log of 1 minus p minus natural log of p, we're going to pull the combine the terms by rewriting it as a quotient, as a 1 minus p divided by p. Then yeah, there's a factor of twos here, these twos, and so on. So we're going to when this guy comes over here, it's going to be 2r times the square root of this energy per bit. So we're going to divide by that 2. That 2 combines with this 2 and comes 4, obviously, and this shows up in the denominator. So this is kind of our governing equation for D1. Now, we could have done it in terms of D2, but we did it in terms of D1. Now, we're going to, again, redefine this as this RTH, or threshold of an R value, right? So in this R space here, that's, again, one-dimensional, so we're just along this real axis here. And we're going to draw this threshold. Now, I just arbitrarily do it right here, okay? And but the exact location is dependent upon this term here, right? And so this is going to be governed by the probability, right? So what we see here is that this has been skewed a little bit, our decision area. We might have, when we think about it kind of in simplistic terms, we would say, well, let's draw that decision boundary right there at 0. If you go back a bunch of slides, I think that's what I did, right? So here I drew it right in between these two things. But again, even though I hadn't even introduced the idea yet, this is for the equal probable type situation. In that case, we would have equal probable, then P would be 1/2, right? So be 1/2 likelihood that you would send S1, 1/2 likelihood that you would send S2. And so you would have 1 minus 0.5, which is 0.5, divided by 0.5. So you'd have 0.5 divided by 0.5. Well, that's 1. Well, what's the logarithm of 1? It's 0, right? So if the probabilities are equal, then we're going to draw our decision boundary right here. This is where RTH would be, right? It'd be 0. Then 0 times coefficient is just going to be 0, right? But if, let's say well, let's do it the way it's drawn. If S2 is much more likely to be sent a priori by the transmitter, right? Not in any given situation, not in any given instance, but in general, if it's more likely because of the structure of the information or whatever, that we're more likely to send S2 than S1, then so this probability is in terms of S1 being sent, right? So if it's higher probability S2 is being sent, then that means that this P is smaller than 1/2. that S1 would be sent, right? So if S2 probability T 2 is greater than half, then that means probability of S1 is less than half, right? So let's just say it's 0.25. So it'd be 1 minus uh, 0.25 would be 0.75 divided by 0.25. Well, that's greater than 1. And so the natural logarithm would be greater than 1, right? So again, this is a situation where we're more likely to be sending S2, right? So this 1 minus P is going to be larger than the probability of sending S1 P. So that's greater than 1. That means the natural logarithm is going to be greater than 0. Greater than 0. By whatever that evaluates to times this thing that's related to the energy per bit and the noise power spectral density, right? So we draw it there, and what we'd be saying is that, well, okay, all things otherwise, then we know that it's more likely that S2 is being sent. So yeah, we'll say that, if we got to guess at which one, right, we're trying to make this estimate, then it kind of makes sense that we would bias this decision boundary over a little bit and say it's more likely that S2 was sent, right? So, all right, so now let's turn that into error probabilities. So, I'm doing on time. What is the probability that impairments cause the received symbol to be estimated in the wrong decision area and therefore mapped to the wrong symbol? We need to know the statistical nature of the random impairments. So let's assume AWGN studied with respect to the noise power and the minimum distance, right? So between the constellation points related to the signal power, the number of symbols, and a constellation design. Right? So we write that using this equation here. So here our probability of error is when we would choose M prime instead of M, right? If M is the true symbol being sent, then what is an error would be when we choose M prime. That means that given that SM was sent, okay, what's the probability of R actually being in this other decision area, right? So we need to integrate this over that whole decision area, right? And integrate that probability of receiving an R value that's inside that decision area, given that SM was sent. Then we need to do it for each M possible, right? So here we're still going to assume a binary type of situation. So there's two symbols possible in our symbol set. Each one has this probability piece of M, right? So the error, again, is when this R would lie in the wrong decision area, right? So we can start to evaluate these, right? Knowing that S is in S sub 1 is the square root of this epsilon B, energy per bit, right? And again, this error is when you send S1, but it lies in decision area 2, right? And that the probability of S1 being sent, this PM, is P, right? And now let's add the probability that, given that S2 was sent, but we laid in decision area 1, right? The wrong decision area. And it's just 1 minus P. So in this two-dimensional, or I'm sorry, one-dimensional situation, these end up just being simple integrals here on this dr. And so we can write this as d2, decision area 2, is ranges from minus infinity up to that r threshold area, right? So we look at here, it's minus infinity up to this threshold. Anything on this side of it out to negative infinity is D2, right? So then we do the same here. Decision area 1 is RTH to infinity. And now we recognize that this is additive white Gaussian noise. So we put in here that this noise really is centered in when S1 is sent, the symbol should be located with a mean at square root of epsilon b, right? So at the energy or the ideal constellation location. But it has this Gaussian noise process about that with this noise power spectral density of n naught over 2, right? And n naught representing the amount of variance in this process, and n naught over 2, right? And that, so the idea is that if, wrong direction. So if there's a Gaussian noise process here, and you're centered here, what's the likelihood that that tail crosses this RTH? Or if we have a Gaussian noise process here, what's the likelihood of that tail being greater than RTH, right? So that's what we're writing out here. This Gaussian process about S2 is greater than that RTH, or this Gaussian process centered around S1 being less than that RTH, right? And then these are all scaled by the probabilities of the symbols being sent. So now we can rewrite this as a Q function, right? And so hang on with me. I know it's we only got a couple of minutes left, but so now we rewrite this as this Q function, and by plugging in the mean value minus the x value of this, Q function, and divided by the square root of the variance, or sigma, right? Variance is sigma squared. And then we do the same thing over here, right? So then this would be the probability of error, and you would be able to calculate RTH knowing the bias terms of the system and the a priori probabilities here, and knowing the energy per bit and the noise power spectral density. So that's similar, related to the signal to noise ratio, right? Just in a little bit different units there. And so then we would look that up in the Q table, and then scale that by the probability of symbol 1 being sent, and then do the same there, and then we can calculate our error probability. So then if they're equal probable, then RTH is equal to 0, and then we see that this is just EB over this, and we can combine these two terms here. So that's 0.5 and that's 0.5 if they're equal probable, and RTH is equal to 0 again. And so we end up with this. So this would be the error probability for antipodal signaling when it's equal probable, right? And you'd be able to, if I gave you an EBNO, you'd be able to look that up in your Q function. That's basically your homework assignment, right? And since K is equal to 1, your symbol error rate is the same as your bit error rate. Okay, so all right, that's it. We'll pick up on Tuesday with lecture 9. So have a great weekend.
Thank you, Professor. Have a good weekend.
Have a good weekend.